Okay, so far we have seen how unintentional program errors can result in vulnerabilities. We saw how buffer overflows work roughly. We'll see more of that later. We saw what happens when you don't have complete mediation or insufficient, when you have insufficient checking. And the last of the three major unintentional errors that you could have is time of check to time of use, or these are also called race conditions. That is, two things are racing and you don't know which one is going to work. Okay, so we saw buffer overflows, we saw basics of incomplete mediation, we saw in the case of web apps, we saw client-side versus server-side mediation checking. And now let's take a look at race conditions. So race conditions, or time of check to time of use vulnerabilities, will result in conditions that may be used by attackers. So let's see what this basic idea is. So normally if you were making a reservation for, let's say, a concert or airline ticket, you would query the front end. So this would be a web application. Let's say you check if a seat is available. The reservation system says yes. Then you book a seat, and then you're done. This person A is done. On the other hand, person B comes along, and this is time. And after person A has booked the seat, if that person A asks, is there a seat available? That seat is gone, maybe that's the last one, and you get the reply back saying no, there's no more seats, and that's good. So this is how things should work. If there's only one seat left and someone checks and finds it and books it, then the seat should not be available to anybody else. Okay, so that's not actually the race condition. This is normal behavior. This is how things should work. Race conditions happen when there's two things sort of happening at the same time. So for example, person A checks, is this one seat available? The reservation system says yes, because it is. And right at the same time, person B asks, is the seat available? So far as the reservation system knows, two people have asked for it, but that doesn't mean either one has booked the seat or reserved the seat. And so it just says yes. And so now person A and person B both think that the seat is available, and they are both able to book the seat. So that would be bad. If we had a system that allowed this, this would be bad. This happens, quite a bit. There might be a lot of people trying to access the same seat or airline reservation or concert ticket, whatever. And if you have a reservation system with multiple people trying to reserve the same thing at the same time, that should not happen. So this is the race condition. Two things happening at the same time roughly, but happening in such a way that the reservation system does what it normally does, but results in two people being able to book the same seat. That should not happen. Okay, so what exactly is a race condition? So when you have two things happening concurrently and the outcome depends on the order in which the instructions from the two are executed. This is also called a serialization flaw. That is, if you did these things separately, they would each do the right thing, but when they happen concurrently, then bad things can happen. This happens very easily in multi-threaded and distributed systems. It's hard to test for these things because this flaw can only show up intermittently. That is, it shows up maybe 1 in 1,000 times or 1 in 1,000,000 times, and that makes it even harder to figure out if this is happening, because if it only happens very rarely, it's hard to recreate this bug, and therefore it's hard to fix. Actually, there are fixes for this, but you have to know about how to use locks, that is operating system locks, using mutual exclusion, condition variables, and semaphores. So these are all built into just about every operating system today, and you can use these. The problem is it's up to the programmer to actually use all of these things, locks, mutual exclusion, mutexes, or condition variables, and semaphores. They have to be used in the right way to make things work. There's no well, there is one way that you can lock everything, but that's bad too. And a lot of things don't work right if you lock everything up. Okay, so we'll get maybe more into that later. Here's an example of things that have happened in the past that have these time of check to time of use type problems or race conditions. The old Unix makedir command creates a directory, but it does it in 2 steps. It first allocates storage for the directory, so it sets up basically a dummy directory, and then transfers the ownership to the user that's executing mkdir, the mkdir command. Once people found out about this, user or malicious or hackers, I guess, figured out that they could start a concurrent process that waits for the first step to be completed and then replace the newly created directory with a link, a symbolic link, to the password file. So you create a directory called harmless and then wait for the first step to be done, and before the second step can be done, you replace that directory with a link to /etc/password. So if you haven't used Unix systems before, this is where all the passwords are stored, and way back it used to be that passwords were stored in plain text. So once you put in this link and the system, the kernel, transfers ownership to the user executing the makedir, now you have access to the passwords of all the people on that system. So if you do this replacement, you make makedir command basically transfer ownership of this file to the malicious user. So these are called time of check to time of use. So that's what this stands for, TOC, TTOU. I know it's a lot to remember, but when you if you think about time of check to time of use, that's probably a good way to remember it. Okay, so these basically happens when some user or process requests a system to perform an action. System checks to make sure that the user is allowed to perform the action, and the system performs the action. So there's 3 steps involved. The state of the system can change between the verification part, that is step 2, and the action or the use, step 3. Okay, so this is the time of check, is the second one, and then the time of use is this 3rd step. So this was used actually recently with the city in what's called the Citibank Casino Cash Caper. People were able to use a certain kind of card in casinos to withdraw money, and they were able to send out their colleagues or their fellow criminals, I guess, to all the other ATMs and casino machines and withdraw the same amount of money, even though they didn't have enough money for all of those withdrawals. So this was something that used to happen a long time ago. It showed up again recently, and crooks figure out these things. Okay, so another example is the Microsoft Passport. This was something that was used a long time ago. I don't think it's used anymore. It used a proprietary Kerberos-like protocol. We'll go over more details of what encryption schemes are used here, but for now, you just want to know that there is an encryption scheme or a scheme for authentication. So it used a protocol like that for logging into a merchant website using a Microsoft account. The problem was, for a time, you could log into this passport system using your account and then change the ID to a different one while the passport system is checking the first account. So the time of check happens, and then while it's doing that, you can change the IDs and you can basically become someone else. And Passport would let you authenticate as the second user effectively. So anyone in Passport could become anyone else because of this time of check to time of use flaw. There was a delay, and you could sneak in some information and exploit that vulnerability. Another example is the old IBM OS 360. So this is going back to I believe the 60s and 70s. They had a file system access control that involved reading the name of a file, comparing its password with what the user entered, and then checking to make sure. So if you had a match, the file name was reread and the access was granted. So here was a critical flaw. If there was no match, you got no access. So you read the file, read the file name, compare the password with what the user entered, and then if there was a match, you reread the name of the file and they grant access to the file that you reread. So a malicious user could take advantage of this time of check to time of use and request access to some harmless decoy file whose password is known. And then while that is being checked, that is, your system is doing this compare of the passwords, you could start or the malicious user could start a background process to check, to change the file name parameter. That is, you check or you make the system check a decoy file whose password you know, and then while it's checking it, you change it. You know it's going to work, and so you change the name of the file to something that you want to get access to, like the list of passwords, let's say, and then the name of the sensitive file is given access to the name of the file with the sensitive file for which you don't know the password. And if the timing worked just right, the system will end up giving you access to that sensitive file, even though you don't have the password for it. Okay, so the password of a decoy file. You pretend like you're going to access that, but then while the IBM system, the file system is checking the passwords and it should work, you say, okay, it's not that file that I want to look at. You substitute in some other sensitive file that you don't have access to, and if the timing worked just right, this file system will grant access to the sensitive file based on the password for the decoy file. Okay. Another problem is undocumented access points. There are trapdoors or backdoors, code entry points that are not documented. So you could have special areas, special ways of getting into areas of a program. You could use these for special access, for example, for testing and development. And this happens a lot. You set up these special test areas of a program, and then just for the sake of testing, and then you forget to take it out when you go into production. So you release some code with all this test software that you forgot about. These things may have unintended consequences, make your code possibly vulnerable to attack, and this may be an intentional vulnerability because someone may have pretended like they're testing it, or they set up special access for testing, but they're actually maybe in cahoots with some criminals, and they're putting in a trapdoor or backdoor for people to use once the code is released. And so this whole problem of trusting trust, you might want to take a look at. You can click on this link, and it'll take you to this classic document on what can you trust in code. Okay, so let's stop here, and then we'll go on with the next part in the next video.